So while we're waiting for others to come, are there any questions from last time? So I want to begin today by answering a couple of questions I've been asked, either in class or sometimes just after class. So one question which was asked is, do black holes violate global hyperbolicity? Well, first of all, let me just draw the Penrose diagrams to emphasize the answer is no. Here's the two-sided version of the black hole with Cauchy surface there, and here's the black hole that forms from collapse, also with the Cauchy surface. So whether we consider the idealized two-sided version of the Schwarzschild black hole or a more realistic black hole that forms from collapse, either way we have a globally hyperbolic space-time. But that underscores what global hyperbolicity says and what it doesn't say. Global hyperbolicity says that the space-time evolves from initial data. It doesn't say how long the space-time evolves for initial data. It says that whatever space-time you've got is what the Einstein equations produced based on some initial data. So the black hole is a case where if you evolve from initial data too far in an appropriate part of the space-time actually breaks down. So global hyperbolicity does not guarantee that you can solve the Einstein equations for all times. It just says that whatever space-time you're talking about is what you got by solving the Einstein equations, starting from some well-posed initial data on some Cauchy hypersurface that satisfied whatever boundary conditions you wanted, such as asymptotic flatness. So that's why there's no contradiction between global hyperbolicity and the existence of a black hole. Then, since we discussed cosmic censorship, I was asked, actually not in class, well, what about solutions with naked singularities? Well, the Einstein equations have all kinds of solutions with naked singularities. cosmic censorship says that globally hyperbolic spacetimes don't have naked singularities. So let's look at the simplest example of a solution of Einstein's equations with a naked singularity. The simplest example is negative mass Schwarzschild. So I'll take minus 2 gm to be positive. So lambda's positive, m is negative. So the metric is ds squared is minus 1 plus lambda over r dt squared plus 1 over 1 plus lambda over r dr squared plus r squared d omega squared. Now you see that G00 is negative everywhere, since lambda is positive. So the traditional monkey business about what happens behind the horizon of a black hole only applies for m positive. So we're now discussing the negative mass Schwarzschild solution, which looks like this, where now lambda is positive. Lambda was minus 2 gm. It has the property that G00 is negative everywhere. So the discussion of the causal structure is completely straightforward. These coordinates cover all of the space-time, but there's a singularity at r equals 0. But r equals 0 is a point in space at all times. So that singularity is on any potential Cauchy hypersurface S. So the space-time isn't globally hyperbolic. There wasn't any initial value surface S from which this space-time would evolve. You could make a partial, let this be the singularity parameterized by t at r equals 0. Then we could take a surface S, but we have to remove the line r equals 0 from the space-time. So this is a partial hypersurface that has a missing point. And then we could make a globally hyperbolic spacetime where we remove this region and also this region. There's no naked singularity because there's nobody in that spacetime that can see the singularity at r equals 0. We had to precisely remove the people who could have seen it. So you can interpret cosmic censorship as the statement that, yes, the Einstein equations have all kinds of solutions with naked singularities, but they're not globally hyperbolic. Or to say it in more physical terms, naked singularities don't form from sensible initial data. That's the hypothesis of cosmic censorship. As I stressed, we don't know that it's true, and it's actually, whether you're happy or unhappy for it to be true, it's a little surprising it's true, if it is true. Because the Einstein equations have the Einstein-Hilbert action has no simple positivity property that would tend to lead to stability. And, well, it's surprising that a theory with such an indefinite action would have good physical properties, I would say. Okay. I think there was one more question I wanted to answer. Ah, yes, okay. Somebody asked, after the last lecture, asked the following question. Okay, we want to prove the area theorem. So, what is the area theorem? It says that as we go from one cut of the horizon to the other, the area of the horizon increases toward the future. And this is a purely local statement. You could bend toward the future just in a small region along the horizon. And no matter where or how you move toward the horizon, toward the future, the area is always increasing. So the statement is really that theta is non-negative everywhere along the horizon. So I was asked whether such statements don't violate time reversal symmetry. After all, the Einstein equations have time reversal symmetry. The answer is that we define the black hole by a time reversal asymmetric condition. The black hole region was Minkowski space after we remove the boundary of the past of an observer at infinity. So similarly, we could define a white hole region where we would remove the boundary of the future of an observer. So there definitely are idealized solutions with white holes. So in the idealized two-sided Schwarzschild solution, this is a white hole singularity down here. It has the property that you can see it, but you can't influence it from outside. The black hole has the opposite property. You can influence it, but you can't see what's behind the horizon. So black holes can form, but we can't eliminate them. That's part of what we proved last time, is that the number of black holes can't go down. It can only, well, black holes can merge, but the future of the black hole region is inside the black hole region, so black holes can't disappear. To the extent that space-time has a future, it always contains black holes to the future. I say to the extent that space-time has a future because, remember, without proving cosmic censorship, we don't know that, according to the Einstein equations, we don't know to what extent space-time has a future. But to the extent it has a future, black holes don't disappear. Just as we can't, just as black holes can't disappear, we can't create white holes. So we've got whatever white holes were present at the beginning of the universe. And the Big Bang singularity is a little bit like a white hole singularity. We don't understand what could have come out of it. So it's not that we say that there aren't any white holes in the universe. We don't understand the beginning of the universe. You could possibly, the beginning of the universe was an enormous white hole in some sense, in the sense of classical general relativity. Anyway, that's the reason that we're discussing statements that aren't asymmetric between the past and the future. We define the black hole region by an asymmetric condition. So now we want to prove the Hawking area theorem. Which says that the area density is everywhere increasing along the horizon. I remind you that theta is the square root of the determinant of the spatial metric. The metric of the horizon was just with 0 times du squared and du dxa. This is not order. The coefficients of du squared and du dxa are 0. So the metric is purely a spatial metric. And then the area density of the horizon is simply the square root of the determinant of the spatial metric. And the claim is that that area density is everywhere non-decreasing. Well, remember the horizon generators. Those are the curves at fixed x, parameterized by u. And we learned last time that those are null geodesics that remain prompt for all u. If we can assume the horizon generators are future complete, in other words, if we could assume that geodesics going to the future from the horizon can be continued indefinitely to infinite values of their affine parameter, we'd simply say as follows. Well, we'd say that if theta equals minus w is less than 0, at some point p in the horizon, then the corresponding horizon generator, which I call L, ends at a known value of u, which was something like u equal to or less than, I think it was d minus 2 over w. But anyway, it was a constant times 1 over w. So if theta was ever anywhere negative on the horizon, that would imply that there's no geodesic completeness for the outgoing null geodesics from the horizon. So it would represent some kind of incompleteness on the horizon. Now, cosmic censorship says that there's no incompleteness outside the horizon, at least informally. And you might want to regard this as a slight strengthening of cosmic censorship, or you might not. If you wanted to strengthen cosmic censorship in that way, you'd have that trivial argument for the area theorem, which I think might be what Hawking originally said, actually. But we can prove the area theorem without assuming that. So here's how we prove the area theorem without that assumption. So, well, here I'm just drawing what's meant to be a spatial cut of the horizon. So it's a codimension 2 space-like surface that we got by cutting the horizon at some value of u, some function u equals f of x gave us a horizon cut. And I'm just drawing it here. And now I'm going to assume that, suppose theta is less than 0 on part of w. Well, if that's true, I'll do the following. I bend w outward a little bit, just in the region where theta is negative. So I get a new space-like surface, w prime, in space-time. It's not entirely in the black hole region, because I bent w out of the black hole region. But I moved w out of the black hole region only in the region where theta was negative. Now, theta is going to vary smoothly when we vary the geometry. So theta is still negative on w prime. Now let's ask if we can communicate with an observer at infinity from w prime. So here's our picture. W was on the horizon. W prime isn't quite on the horizon. And here's an observer at infinity, or the world line of an observer at infinity. Can we communicate with the observer at infinity from w prime? Well, the answer must be yes, because w prime isn't in the black hole region entirely. So there are points in w prime from which we can communicate with infinity. But now we're about to reach the usual contradiction. Using compactness of spaces of causal curves in a globally hyperbolic space-time, if we can communicate with the observer at infinity, we can minimize the time at which such a signal arrives. So if there's any causal curve gamma, so if there exists a causal gamma from w prime to I, then can pick gamma to be prompt. And therefore, you see, okay. If you take any sequence of causal curves that arrive sooner and sooner, there will be a limiting causal curve that arrives as promptly as soon as possible. That one will be prompt more or less by definition. And then gamma is an orthogonal, well, a null geodesic orthogonal to w prime with no focal point. And here we're going to get a contradiction. Gamma can't originate from the part of W prime that is on W, because that's in the horizon, and no causal curve from the horizon goes to infinity. Gamma also can't originate from the part of W prime outside of the horizon, because theta is negative there. So the orthogonal null geodesics from those points reach focal points at some bounded value of the affine parameter. So if we move I sufficiently far away, then you can't possibly communicate with the world line I from anywhere on W prime. So the only way out is that theta was not negative anywhere on the horizon. So that's the Hawking area theorem, and it's one of the most important results I've told you about because it's the kind of classical limit of black hole thermodynamics. Since, as we'll discuss later, the area was interpreted as a classical limit of the black hole entropy, and the fact that the area is non-decreasing became interpreted as a classical limit of the second law. So any questions about this discussion of the Hawking area theorem? Yes?
Is there anything analogous that can be said about horizons in cosmology?
Everything I've said actually makes sense. So, okay. What is a horizon in cosmology? So, first of all, the notion of horizon in cosmology is observer dependent. You have to pick a particular observer, let's say with this world line. Then, well, I'm not sure black hole region is always a good terminology, but the region we define, I'll call it the black hole region now. We make the same definition. It's observer dependent, but nothing I said about this setup depended upon asymptotic flatness. The only thing that really depended on asymptotic flatness was that it wasn't important which observer we picked. In an asymptotically flat spacetime, any observer more or less at rest at infinity, not highly accelerating, will lead to the same black hole region. In cosmology, you can make the same definition, but it will be more observer dependent. We could illustrate that with the example of de Sitter space. I wasn't planning to, but we definitely can. Maybe I will, actually. So I think I will in a second illustrate that with the example of de Sitter space. So the definition makes sense, and the proof of the area theorem applies. So everything we've said makes sense for horizons in cosmology, except the physical interpretation is a little different because it's much more observer dependent. Let's just very briefly discuss that in the case of cosmology, de Sitter space. So remember, this was the de Sitter metric. It exponentially blows up for t goes to plus or minus infinity. And, well, the future part of that blow-up is believed to be an approximation to the present universe. As far as we can see, there's a very small positive cosmological constant, and it appears we're starting to enter a period of exponential expansion. And within 10 billion years or so, it's believed that this may well be quite a good approximation to the present universe. Well, the future of the universe we're living in. Anyway, the Penrose diagram looks like this, where t equals infinity is at the top, t equals minus infinity is at the bottom, and the south and north poles on the sphere, this is the metric of the sphere. The south and north poles of the sphere are drawn on the left and right. And what the figure is showing us is that if you start on the left at if you start at the south pole at time minus infinity and go at the speed of light, you'll barely reach the north pole at time plus infinity, and vice versa. So there are lots of fun things about this picture we could discuss that would illustrate things we've proved in the course. Some of them that I wasn't planning to explain are actually in my lecture notes. But concerning the question, now let's consider an observer. Sorry. Well, okay. Let's consider an observer at the South Pole. That's the one we can see most easily in this picture. Then for that observer, the lines I just erased are the past and future horizons. So we usually are interested in the past horizon, the future horizon, sorry, what you can't see beyond. So this observer will never see past this line and can never influence what was to the past of this past horizon. Likewise for this, so this is the horizon for an observer in the south, this is the horizon for the observer in the north. You could ask about another observer. My picture isn't quite adequate. The other observer wasn't, remember in the picture, the polar angles in the sphere are suppressed. But the observer who lives neither at the north nor at the south pole lives at some value of the polar angles, which aren't shown in this picture. If we were in 2 dimensions, though, that wouldn't apply. So let's continue in 2 dimensions. Then the metric is still correct in 2 dimensions, and then there aren't any polar angles. Then this is a more complete depiction of the whole 2-dimensional de Sitter space. For this observer, the future horizon would look like that. You wouldn't see beyond these regions. And the area theorem would say that the area of that horizon is non-decreasing. And in fact, that area is constant, as you'll see with a little bit of work, or a little bit of thought. I think you can find it discussed somewhere in my lecture notes, maybe in an appendix. That's actually, I think, all I'm planning to say about cosmological horizons. In theory, we could get back to de Sitter space at the end of the course, but I think we will run out of time. Any other questions? About what?
About this example of the system.
Yes?
Maybe I'm misremembering, but what happens if you have a black hole in the center? Then after 3-dimensional process where you're increasing the mass, I thought that the area of the cosmological horizon decreases.
Well, it doesn't decrease in time. You're comparing 2 different solutions.
Yeah.
Okay.
Yeah, I guess it's a process where it's a matter of volume of the black hole.
Well, I'm reluctant to go into detail because it involves a lot of things we haven't discussed. But roughly speaking, the initial state has matter and a cosmological horizon of lower area and no black hole. Then in time you form a black hole which adds to the cosmological horizon. Anyway, you're not going to contradict the area theorem. Any questions otherwise? Okay, now we're going to, if there aren't more questions, we'll move on to something else, well, some things that I think are fun, which will be topological censorship and the Galois theorem. So first, topological censorship. So this has to do with wormholes. Well, what's a wormhole? Well, it's the science fiction idea of a shortcut between 2 widely separated regions in space, or possibly between 2 different universes. So there sort of are 2 kinds of wormholes. In one case, we don't have to assume asymptotic flatness. We could assume asymptotic something else. We need some kind of asymptotic condition to define what we're talking about. And for brevity, I assume asymptotic flatness. So in one version of the wormhole, we've got actually 2 different asymptotically flat universes that are connected by a wormhole. So the initial value surface looks something like that. Far away, it looks like, if we're in 3 + 1 dimensions, it looks like R3. In the interior, there's a hole, a little wormhole. If you go down the wormhole, you come out in another universe. At least the initial value surface does that. Now, there's another version. These are presumably both fit for science fiction, but the other version is that there's a shortcut from us to Alpha Centauri. There's a hole somewhere in the Milky Way galaxy. There's a hole somewhere in Alpha Centauri. And there's a shortcut that connects the Milky Way to Alpha Centauri. Now, we're going to, so first of all, the Einstein equations definitely have solutions where the initial value surface has a wormhole. I'll mention a famous one in a second. Yes?
Sorry, what are the only defining as a wormhole? Is that like a shortcut, or like it's not a topological definition, or it's just...
Well, I've given basically a topological definition. So, but to state it in more mathematical terms, this one, S has two ends. End is a technical notion in topology. But to state it informally in this context, I think you know what an asymptotically flat end is. So here, S has two asymptotically flat ends. In this example here, the fundamental group of S is non-trivial, because you could go the long way from the Milky Way to Alpha Centauri, but then you could come back through the wormhole, and that would be a topologically non-trivial path that would represent a non-trivial element of pi1 of S. So either S has multiple ends or it has non-trivial fundamental group. So there's no problem in general relativity to find classical solutions that have wormholes in the initial value surface. But that shouldn't satisfy any science fiction writer. What you want to know as a science fiction writer is whether you can go through the wormhole. So we know that general relativity, bad things can happen to space-time. Singularities can form. So if you go in the wormhole, can you actually come out the other end before it closes? A wormhole that collapses faster than you can go through it at the speed of light is interesting as mathematics and physics, and might tell us important lessons about gravity, but it's not useful for science fiction purposes. Now, topological censorship says that we can never go through the wormhole, assuming the null energy condition. Topological censorship says that given the null energy condition, which is, I remind you, that TU is equal to or bigger than 0 at each point and in each local Lorentz frame, we can't go through the wormhole. Now, before proving this, let me just explain the motivating example for topological censorship. The motivating example is Schwarzschild. Sorry, even before I say that, though, I wanted to say something back here. Sorry. I'll get back to that in a second. So there are two things that you might mean by wormholes, but we can study them together because we can replace, in the classical analysis that I'll give, we can replace S and M by their universal covers. And thus, we can reduce to case A. So there are two types of wormhole. But in the second case, the shortcut from here to Alpha Centauri, space-time has a non-trivial fundamental group. You could take the universal cover of both the initial value surface and the whole space-time. The Einstein equations would still be obeyed, and you would have a wormhole of this type. And obviously, whether you can go from, in picture B, whether you can take the shortcut, is the same as in picture A, whether you can go from one universe to the other. So instead of stating the mathematical arguments twice for case A and case B, it will suffice to state them just for case A. And that has the advantage that the motivating example is easier to explain in case A. The motivating example is Schwarzschild. So I'll draw again the Penrose diagram. for the maximally extended Schwarzschild solution. So here's our Cauchy hypersurface S, and it has got two regions at infinity. So let me remind you that there's a d-2 sphere that's not drawn on the diagram. And the metric, so well, there are two coordinates that are drawn on the diagram. They're null coordinates in the sense that increasing u at fixed v and increasing v at fixed u are both radial null geodesics. And then the metric looks like this with some function r of u and v. And we mentioned some values of r previously. So r is infinity at infinity. It's 2gm on the horizon. It's 0 at the singularity. The same is true on the past singularity and the past horizon. But importantly for today's purposes, r also goes to infinity on the left. So what is actually an initial value surface in this maximally extended Schwarzschild spacetime? Well, qualitatively, let me indicate something that would qualitatively be correct, although it's not exactly correct. Maybe I'll call this parameter rho. Rho is not r. Rho is r at infinity. Otherwise, rho is a different coordinate. Rho runs from minus infinity to infinity. Rho is plus infinity on the right and minus infinity on the left. So what I've written here, except that the function rho squared plus a squared is not exactly right, is the geometry of a slice of time symmetry in the Schwarzschild solution. A particular S that we pick to be invariant under t going to minus t. So you see, it's exactly this wormhole I've drawn here. Rho is infinity up here, and it's minus infinity down here. This picture actually is due to Einstein and Rosen. The Einstein-Rosen bridge is the wormhole between the two worlds. However, Einstein and Rosen didn't discover the time-dependent version of it. So they didn't discover that you can't go through the wormhole. That's what we learned from this Penrose diagram. If you start on the left in the far past, that would be down here, and you go even to try to go through the wormhole, that means you go to the right at the speed of light. But even going at the speed of light, you end up at the singularity at r equals 0. Likewise, if you start on the right and go to the left, you'll end up at the singularity at r equals 0. So the Schwarzschild solution, maximally extended, is an example of a spacetime with a wormhole. But this is what people call a non-traversable wormhole. Even traveling at the speed of light, you can't get through the wormhole from one side to the other. So the question of cosmic censorship, or well, the statement of cosmic censorship is that this is generic. That assuming the null energy condition in any spacetime with a wormhole, you can't get from one side to the other.
So
Yes?
I guess one could still see the other universe before you sort of hit the singularity, yes?
No. Oh, yes, you can see it. That's right.
So
That's right. As you go through, you can learn or become convinced the other universe exists because you can see stars and galaxies out there, but you can never visit them. Any other questions? Yes?
I have a basic question. So the wormhole that we drew on the left,
Yes.
That also, like, doesn't that have non-contractible cycles?
No, because, well, that wormhole, the geometry was here, so the topology is R times a sphere. The sphere is just the sphere labeled by the polar angles. And R is parameterized by rho.
So if we take D equal 3, in that case,
In D equals 3, it has a non-trivial fundamental group. For generic D, it does not. For D equals 3, it has a non-trivial fundamental group, but unwrapping that, okay. My statement, okay. I didn't, in general, say that this one can't have a non-trivial fundamental group. It can. It doesn't have to. This one has to have a non-trivial fundamental group and has the property that you can partially unwrap it to go to this picture. In the case, okay. In the case you're mentioning, I'd rather not completely unwrap it because that would, I'd like to keep it asymptotically flat with a standard form at infinity. So I don't want to really unwrap the theta angle. Any other questions? So up to a point, the proof of topological censorship is the same argument that we're always making. In fact, one thing I hope you're learning from these lectures is that there are just a few ideas based on which you can prove a lot of nice things in general relativity. Anyway, well, I'm going to draw two pictures, the left and the right, two asymptotically flat regions. In the right, we're going to have the world line of an observer at infinity. Well, let's say a world line at infinity. In the left, I'm going to have a space-like hypersurface at infinity. This is a codimension 2 space-like surface at infinity. So to be a little more specific about what W is, the metric is approximately the Minkowski metric near R equals infinity. That's what asymptotically flat means. And W is roughly, this doesn't have to be exactly, T equals T naught, R equals R naught. Except that I want to keep T plus R fixed. So let's say T equals minus, let me say T equals minus T naught plus K, R equals T naught. So T plus R is K is called the advanced time. The meaning of the advanced time is that it's the time at which, if we were actually in Minkowski space, a signal from W would reach the origin. So now what we want to claim is that no matter how negative is the advanced time, a signal from W can't reach the observer at infinity, no matter how long the observer at infinity waits. So it's a little hard to draw the picture, and it's even harder to draw it in space-time. But the question is, can a signal from W go through the wormhole and reach the observer at infinity? That's at least a picture of what's happening in space without trying to draw the time aspect. So we're going to prove that the answer is no, assuming the null energy condition. So we've got the same setup as in the proof of the area theorem. We have a codimension 2 space-like surface, and we want to know if we can send a signal to a world line, a time-like world line. And you know we're supposed to do the following. If we can send such a signal, we can send it in a prompt fashion. And so if a causal curve gamma from W to I exists, we can assume gamma is prompt. And that means that gamma is a null geodesic with no focal point. and also orthogonal to W. Well, W is a big sphere near infinity in almost Minkowski space. So orthogonal null geodesics go either out or in. The ones that go out just escape to infinity in the left. So they're not going to go through the wormhole. The ones we have to consider are the ones that are going in. They're going towards the wormhole, and our question is, can one of those orthogonal null geodesics that's going in go through the wormhole and come out the other side? And if it starts from exactly the right point on W, eventually intersect I. The guys that are going in have theta negative, because basically we have a big sphere in Minkowski space. We're looking at the incoming null geodesics. And the incoming null geodesics have theta negative. And since W is compact, well, it's uniformly negative, we can give an upper bound on the affine parameter to which any of those can be extended before reaching a focal point. I, on the other hand, can be as far away as we want. And so I can be so far away that you can't reach it except by extending to a bigger value of the affine parameter. So we conclude that gamma doesn't exist, and topological censorship is true. I hope that simple argument convinces you that the things we've been discussing are worth knowing, if only to debunk science fiction. Any questions about it? Yes?
I'm not sure if this is true, but considering the case that the average non-linear equation is not satisfied, is it possible to go to the wormhole and achieve a quickest time that not using the wormhole at all? In the case B, for example.
Our argument applies equally well to case A and B. I stated the argument for A. I could have stated it for B. The way I would have stated it for B, I'd have considered homotopically non-trivial paths from a sphere at infinity to a world line at infinity. And then I would have said all the same things. So we didn't need to... I used the fact that mathematically we could take the universal cover, or A cover, and replace B by A to avoid discussing B separately. But if you think about it, the argument we give could easily be adapted for B. I'm not sure I understood the question, however, so ask again.
I'm asking the case that the average non-linear equation is not...
I'm going to, well, first of all, we haven't discussed the average null energy condition. We've discussed the point-wise null energy condition. We've discussed the null energy condition. What we used here was the classical null energy condition, which is that this is positive at all x and all local frames. In other words, d by du is any null direction. So what we've assumed so far is the classical null energy condition. And statements we proved previously in this course, like the Penrose theorem, everything we've proved up to this point requires, well, at least in the form in which we stated them, everything we've proved requires the point-wise classical null energy condition. However, as the questioner perhaps had in mind, topological censorship, it turns out, can use a weaker condition. The weaker condition is called the average null energy condition. Well, what's the average null energy condition? You consider a null geodesic gamma that's complete in both directions. With affine parameter u that goes from minus infinity to infinity. That's the statement that this is complete in both directions. And then the average null energy condition is that the average of the null energy over the world line, over the geodesic, this is the integral on gamma. So gamma is parameterized by u. So when I say integral du, I mean the integral on the geodesic of tu is equal to or bigger than 0. So the average null energy condition says that the average of the null energy along the geodesic is non-negative. Now, Tuesday will prove if the ANAC, average null energy condition, is often abbreviated as ANAC. If the ANAC is true for gamma, then a sufficiently big piece of gamma is non-prompt. Actually, I'm not sure if I will. I might only prove that. I might only prove this slightly weaker statement, that this is true if the ANAC is true as a strict inequality. The case where it's the ANAC integral is 0 rather than positive is trickier to prove, and I think I may not do it in the lecture, so I might leave you to look in my lecture notes if you want to see that refinement. But anyway, it's true that if the ANAC is true for gamma, then a sufficiently big piece of gamma is non-prompt. Now, if you go back to this argument, you'll see that that means that the ANAC was good enough. Because by moving W to the farther away, keeping the retarded time fixed, the advanced time fixed, and by moving I farther away, we can force ourselves to look at a bigger and bigger piece of gamma in both directions. And eventually gamma will become non-prompt because of the result that we'll prove Tuesday. And that's what we needed in this argument. So with the help of Tuesday's argument, we will learn that the topological censorship only requires the ANAC. It doesn't require the point-wise classical null energy condition. Since I think on Tuesday I might only prove the case where the ANAC is a strict inequality, I think I'll remark that that's good enough for this application. So the statement on this blackboard is also true. It's true, and you'll find out Tuesday that it's equivalent to a funny statement in quantum mechanics. But it's harder to prove, and I might not prove it. But I'd like to remark that we don't need that quite slight refinement here. Suppose that the ANAC integral is strictly 0 for gamma. We could make an infinitesimal perturbation, for example, by adding some dust near infinity in one of the two regions. Then the ANAC integral would become positive, but an infinitesimal perturbation wouldn't affect the ability to travel through the wormhole. So even if I only prove this statement on Tuesday in the weaker sense of a strict inequality, that's actually good enough to imply that that topological censorship only requires the ANAC and not a point-wise condition. Any questions? However, I want to say a few more words about what the ANAC means. We've just been doing classical relativity. So in classical GR, the ANAC makes sense, but sounds strange. If it's not true that TU of x is positive for all x, why would we miraculously have the Anneck integral positive. In other words, classically, if you have a classical field theory where it's possible for TUU to be locally negative, you'd expect that there are field configurations where the integral of TUU is negative. There aren't really physically sensible field theories where, anyway, the pointwise condition isn't true classically, so the question's a little bit counterfactual, but it sounds strange, very strange classically. Quantum mechanically, though, it is more interesting. Quantum mechanically, the statement is usually interpreted, the Anneck is usually interpreted to refer to the integral of the expectation value of the stress tensor in some quantum state. That's the quantum statement of the Anneck. So that's what the Anneck is usually taken to mean quantum mechanically, but in general that statement is not true. So, sorry, okay. To state it a little bit more exactly, you want to physically, you imagine, well, you want to have a physically sensible quantum field theory. It doesn't have to arise by quantizing a classical field theory, but it might. You can imagine a classical field theory where TUU was non-negative pointwise. However, the quantum it's not true that the quantum TUU is non-negative pointwise. Maybe I should take time to prove that, but I'm afraid of running out of time for this lecture. I hadn't worked that into my plans. But sometimes you can prove quantum mechanically that although TUU is not positive pointwise, its integral in a null geodesic is positive under some conditions. And that kind of statement is what people mean by the Anneck. However, it's not true in general. That the quantum Anneck with that statement is not true in general. So there's a simple example that has come up a few times in our course. A two-dimensional metric on a cylinder, minus dt squared plus d sigma squared, is the metric where sigma is an angular variable. Then we can have a null geodesic that wraps around. I gave this as an example of a null geodesic that wasn't achronal. And we could even perturb it to make it space-like and not achronal. So this example was a counterexample to various things that we mentioned before. It's also a counterexample to the most naive version of the Anneck, because a quantum field on the cylinder can have a negative Casimir energy. And then the expectation value of TUU in the ground state is negative. And integrating won't help because in the ground state TUU is a negative constant. So the Anneck isn't true universally. On the other hand, the Anneck is true for a null geodesic in Minkowski space. I'm hoping to explain one of the proofs of that, but I'm not sure we're going to have time, actually. So, in between the fact that it's not true in general and it is true for a null geodesic in Minkowski space, the status of the Anneck isn't known, but it's conjectured true if gamma is achronal and the space-time is self-consistent. Self-consistent simply means that that the Einstein equations are obeyed with sources given by the expectation value of the stress tensor in some matter state. So our example with the cylinder was self-consistent because r mu nu was 0. Well, okay. We could make the example self-consistent if we adjust. Well, okay. Our example wasn't quite self-consistent because t mu nu is non-zero, which led to the difficulty here. And I assumed the metric was flat. But that's actually inessential in this counterexample. So you could modify this counterexample slightly to make it self-consistent, and it's still a counterexample. Now, we're not really, okay. We're usually assuming self-consistency when we interpret the Einstein equations as classical equations. That's a little bit stronger than assuming quantum self-consistency in this sense. So self-consistency in that sense is an implicit assumption throughout the course. And in this setup, gamma can be assumed to be achronal because if it stops being achronal, it's not prompt, and then we would have had the contradiction again. So this version of the ANAC would suffice to prove topological censorship, but as I've told you, this version of the ANAC is only a conjecture. It's not known to be true. So to summarize, we have the ANAC based on the classical null energy condition. Sorry, I don't remember what I said. We have topological censorship based on the classical null energy condition. We also have topological censorship based on a classical version of the ANAC, but that depends on something we'll prove Tuesday. And we would have a stronger version of topological censorship based on this quantum ANAC, but the quantum ANAC is only a conjecture. Any questions on that? I think next time I'll explain the statements that in quantum field theory the energy density isn't positive definite, so that the null energy condition in quantum field theory doesn't hold as a pointwise statement. I don't think we quite have time to do that today, even though it's a very short argument. Because I want to use the remaining time to discuss the Gell-Wald theorem, which is causality in ADS CFT. So we previously discussed the ADS2 geometry. We used it to illustrate various, we wrote the ADS2 metric in this form where sigma goes from 0 to pi. And so the metric was a strip. Time runs vertically, sigma runs horizontally, sigma 0 on the left and pi on the right. And in our previous discussion, it was important that the boundaries are not in the space-time because of the 1 over sine squared sigma factor. So the metric, we can't include those boundaries and have a smooth metric. In fact, in a spatial direction, these boundaries are infinitely far away. So they're actually called conformal boundaries. They're not in the space-time, although they are in a conformal compactification of partial compactification of the space-time that's suggested by the picture. And then we use this, well, we discussed the behavior of both time-like and null geodesics in this spacetime. In particular, the time-like geodesics from a point Q all focused at a point P, and we had some fun with that and related statements. However, today we're going to do something else. And for today, we're going to generalize to D dimensions. So first of all, in D dimensions, the topology of ADSD is R times B D minus 1. B equals an open ball. For D equals 2, D minus 1 was 1, and the open ball is just the open interval where sigma goes from 0 to pi. In higher dimensions, we instead get an open ball. Many of you will be familiar with ADSD already. If you're not, you can read a little bit more about it in my lecture notes. But I'm going to try to give an explanation today that doesn't require too much knowledge. I'm going to draw the picture, though. Here's an open ball B. Well, here's B. And here's the boundary of B, which is a sphere, a D minus 2 sphere. And that's the conformal boundary, well, which also include time, which runs vertically. But anyway, SD minus 2, R parameterized by the time times SD minus 2 is the conformal boundary. And that actually is, a portion of this is equivalent conformally to Minkowski space of dimension D minus 1. This is sometimes called the Einstein universe. It's a sort of conformal extension of Minkowski space. Now, what's called the ADS-CFT correspondence, what the conjecture, as I stated, was formulated by Maldacena in 1997, states that a quantum gravity theory in ADSD. Now, that's a turn of phrase that's occasionally misunderstood. In quantum gravity, you never specify the space-time. The space-time is fluctuating. You specify only the asymptotic behavior of space-time. So what I mean by conformal quantum gravity in ADSD is quantum gravity in spacetimes that are asymptotic at spatial infinity to ADSD and do whatever they want in the interior. But for brevity, I call that a quantum gravity theory in ADSD, is equivalent to a conformal field theory. Now, conformal field theory means an ordinary quantum field theory on the conformal boundary, which I think I'll call M. So the claim is that we can do ordinary quantum field theory, which you perhaps study in your quantum field theory courses in the department here, on M. Or you can do quantum gravity, which supposedly is that incredible mysterious theory we don't understand, in ADSD. And they're claimed to be equivalent to each other. And even 25 years after the original conjecture, it's still a very perplexing statement, but it's held up beautifully and certainly appears to be true. And the Galois-Wald theorem explores one aspect of how it's true. Galois-Wald asks, is this duality consistent with causality? Well, what do I mean by that? Let's first discuss what causality means in the boundary theory on M. You have a point Q and another point P, and you ask, can an event at P influence something happening at Q? You all know the condition for that. For an event at Q to influence P is equivalent to having a causal curve gamma from Q to P. This is a causal curve gamma in M because we're exploring causality, first of all, in the boundary theory. So that's just a statement about relativistic field theory in M. Now let's consider it in the context of the claimed duality with quantum gravity in the bulk. Well, remember, okay, a classical fact that underlies this duality I actually explained in possibly the first lecture, which was that, so we explained it in 2 dimensions, but it holds in any dimension. Although the boundary is infinitely far away, you can reach it in finite time along a light ray. So in bulk, the way Q would influence P is that you could have a causal curve in the bulk, I'll call it gamma tilde, that arrives at P. So in the bulk, you'd ask, is there a causal curve gamma tilde from Q to P? A path that goes through the bulk, it starts at Q on the boundary, ends at P on the boundary. But now, what would it mean to violate causality? We'd violate causality, or more exactly, the bulk theory would appear causal but would violate boundary causality if we have gamma tilde from Q to P tilde, this is in the bulk, where P tilde is to the past of P. In other words, so this picture where the bulk curve arrives at the same time the boundary curve arrives is consistent with causality. What would violate causality would be if there's another boundary point, P tilde, to the past of P, and there's a shortcut in the bulk that arrives at P tilde, which can't be reached by a causal curve in the boundary. So ADS-CFT duality is in danger of contradicting the causality of the boundary theory if there's a shortcut in the bulk. If a causal curve in the bulk can do something that a causal curve in the boundary can't do, connecting 2 points that are space-like separated in the boundary, then the duality would be inconsistent with causality. So the Gall-Wald theorem tells us that this doesn't happen. Well, how do we prove it doesn't happen? Well, you see, I always tell you the same thing over and over again. So P tilde is to the past of P, so there's some time-like world line in the boundary from P tilde to P. We can continue it in the past and future. There's a world line I in the boundary. Now, by hypothesis, from Q you can communicate in the bulk to that world line. So then, if there's a shortcut, there's an optimal shortcut that would... So if gamma tilde exists, there is an optimal gamma tilde where P tilde is as far to past as possible. I hope by now you've gotten the hang of it. If you're trying to prove something doesn't exist, you ask about the worst thing of its type. And then you show that it violates Regidori's theorem or something else you already know. So the worst gamma tilde is prompt. So it's a null geodesic with no focal point. With no focal point. Now, gamma tilde goes from the boundary of ADSD, conformal boundary of ADSD, to the conformal boundary. And that implies that it's complete. But that point is a little subtle and needs explanation. As I've told you, a null geodesic can reach the boundary at finite time. Actually, for what I'm going to say, it doesn't matter if we're in 2 dimensions or higher dimension. So, in the 2-dimensional version, which we've discussed in more detail, the null geodesics are just the lines at a pi over 4 angle to the vertical, and they certainly reach the boundary at a finite time. But although they reach the boundary at a finite time, the affine parameter along one of these geodesics goes to infinity at infinity. So to show that, you have to do a small calculation, which I think I'll do. I hope I can do it and finish the lecture today. Well, I'll do the calculation, but I'm going to write the metric near the boundary. I'm going to write a local form of the ADSD metric near a boundary. So the local form so I expect that a fair number of you are familiar with this local form of the ADSD metric, some not. If you're not, well, in the 2-dimensional case, if you drop the x's, which wouldn't be there, and let sigma be r, then you can see that this metric looks like this near r equals 0. But if you're not familiar with this form of the metric, you might want to look up the derivation of it, possibly in my lecture notes or someplace else. Now, this is a homogeneous space, so it doesn't matter what null geodesic we pick. So for an example of a null geodesic, we can pick the one at x equals 0 and t equals minus r. So that geodesic goes over the region from minus infinity less than t less than 0. It reaches the boundary at t equals 0, and we want to show that the affine parameter diverges. Now, to get the geodesic equation with an affine parameterization, you use this action. Well, in general, you use the action in general, okay. I want to write down something about the geodesic equation with affine parameterization. Just as a reminder, one way to find that equation is to start with this action, and then the Euler-Lagrange equations will give you the geodesic equation with an affine parameterization. In our case, I've set x to 0, and I've used the part of the metric that's relevant for a geodesic at x equals 0. So we have this action, and then there's a symmetry, t going to t plus a constant. So there's a conserved quantity, q, which is 1 over r squared dt du. And we'll set, so q is a conserved quantity, and it could be anything, but we could rescale the affine parameter u to set q equals 1. By rescaling u. I remind you that on a null geodesic, the affine parameter is only defined up to an affine transformation that includes a rescaling. And also, we want this geodesic where t is minus r. So we have 1 equals minus 1 over t squared dt du. And we can solve that to get, plus 1 over t squared dt du. We solve it to get t equals minus 1 over u, or minus 1 over u plus u naught, I think. Oh, sorry. So we see that u goes to infinity as t goes to 0 from below. So we prove that a future-going null geodesic that reaches the boundary of ADS is future complete. We use the ADS form of the metric, but that was legitimate because we're assuming an asymptotically ADS spacetime where the metric is ADS near the boundary. The same calculation would show that a past followed into the past, a null geodesic that reaches the boundary is complete. So so the shortcut that violates causality, we can assume is a complete null geodesic that's prompt. However, the ANAC would imply, well, okay. So we'll prove next time. We'll prove next time that, as I said, that if the integral of TUU is positive, then a sufficiently big piece of gamma tilde is not prompt. Which would contradict this setup and show that gamma tilde can't exist. As I've remarked, it's also true if the integral of TUU is 0. Although I might not explain the proof Tuesday, but for this application we don't need it. If causality was violated, any slightly different spacetime would still violate causality. So you could sprinkle a tiny amount of dust. If the ANAC integral is strictly 0 on gamma tilde, you could sprinkle in a tiny amount of dust near the boundary, where it would do nothing much except to make the ANAC integral slightly positive. Then you'd have the same contradiction. So, although I think I may not prove the case where this is 0, for this application we don't actually need to know that. So the ANAC would tell us that ADS-CFT can't violate causality. In particular, classically, ADS... Now, we don't really know if the ANAC is true. So we're in the right setup where the conjecture about the ANAC would apply, but we don't know that that conjecture is true. So gamma tilde is prompt, which implies that it's achronal, and we're only interested in the case where the spacetime is self-consistent. So if the quantum version of the ANAC conjecture is true, we would deduce that ADS-CFT is consistent with causality. At any rate, in the classical limit, which in the context of ADS-CFT means what's called large N, we are okay because we have the pointwise condition. So we don't really have know, as a theorem at least, that the general self-consistent ANAC is true, but at least we have the classical version of the Galois theorem that for a classical spacetime, in other words, in the large N limit of ADS-CFT, there's no violation of causality. Okay, I think I'll just stop here and ask if there are any questions. Yes?
So this is also proof that there are no geodesics between Q and P throughout the ball?
A more careful argument shows that that's true, that there's none. But what we proved is that there's no geodesic from Q to a point to the past of P.
But if you at some point use it on and construct this line, couldn't, okay, I guess it would coincide and there's no line.
What's your question?
So it just seems like this is very close to proving that there is no gamma soda between Q and P.
Well, a more careful argument shows that,
Okay.
no, actually that isn't true in general. For ADS exactly, there is a geodesic from Q to P. What the argument proved is that there's no geodesic from Q to the past of P.
Okay.
Okay, you see. What the argument, okay. There was a step in the argument where we made an infinitesimal perturbation to make the Banach integral strictly positive. Okay, sorry. For essentially anything, when the Banach integral is strictly positive, there's no, the argument as I stated it proved that there was no geodesic from Q to a point in the past of P. If you want to know if there's a geodesic in the bulk from Q precisely to P, you have to be more careful with the arguments than I've been in the lecture.
Okay.
And I might have trouble straightening it out in real time, especially since we're over time.
Yeah, okay, but would the same happen well then for side to the future then?
There's no problem getting to the future.
But could I also then draw a line I as you did and say there's, I mean,
No, finish your question.
no, it's just
I exist for all times.
yeah.
And the space-time could be assumed to be simple enough topologically and causally so that you can definitely communicate from Q, either in the bulk or in the boundary, to any I at sufficiently late times.
Yeah.
The question we're addressing is whether through the bulk you can send a signal to I that arrives sooner than a signal would have arrived in the boundary. What we proved under the either classical or quantum Banach, depending on what you want to assume, is that you can't do better in the bulk than you can do in the boundary. We weren't careful enough to decide whether you can do as well in the bulk as in the boundary, and that's subtle enough I don't want to discuss it now. Any other questions? Okay, then I'll see you Tuesday, and what are we going to do Tuesday? Well, first of all, we'll discuss what's the last section in my lecture notes in case you want to read about it. We'll discuss the relation between null geodesics and the Schrodinger equation. And there will be mainly two goals. The general goal, it was extremely important in all this to know that a light ray stops being prompt when it passes the focal point. And we proved that to the extent we proved it with pictures. On Tuesday, we're going to prove it using the Schrodinger equation. And then there's a specific goal Tuesday, which is that I used today the assertion that when the Banach integral is positive, a sufficiently large piece of a null geodesic isn't prompt. So that's part of what we'll prove on Tuesday. And Tuesday we'll be finished with general relativity. After that, we're going to be doing quantum field theory.
Quick question.
Yes?
I was told at some point that the maximally extended Schwarzschild